All right, so let's see what we have. It says at the starting gun, a runner accelerates at 1.9 meter per second square for 5.2 seconds. The runner's acceleration is 0 for the rest of the race. What is the speed of the runner at t equals 2 seconds and also at the end of the race? All right, so one thing you want to, I guess, identify when you're looking at a problem like this is what type of problem is this? Is this one-dimensional kinematics? Is this two-dimensional kinematics? Is this, let's say, Newton laws of motion, right? Is it basically Newtonian dynamics? Are there forces involved? So what do you guys think? Who can help me here? What type of problem is this? How would you categorize this problem?
The kinematics problem?
Kinematic.
Yeah, is it one-dimensional or two-dimensional?
One-dimensional.
One.
Exactly, one-dimensional, which means what we have here is, I like to do always a rough sketch. So let's say this is the race going from point A to the end. But here's the thing: we have two parts because it says that it starts from the from rest, right? At, let's say, position A. It then accelerates for 1.9 meter per second square, but it accelerates for 5.2 seconds. And after that, its acceleration is 0, which means whatever speed it has at the end of the 5.2 seconds, it's going to then move at that speed the entire time. That means, in a way, we have 3 points of interest. Point A to point B, then from point B to point C. All right. Now, what I have here is from A to B, then there is acceleration. There's an acceleration, which is equals to 1.9 meter per second square. So our runner going from A to B basically accelerates. So let's make this, let's say here's a runner. I'm going to make it up as a particle. That means going from, where velocity at A is 0, because it starts from rest, because, right? Starting at gun, that means you start from rest and you start accelerating. Then you're going to get to position B. Now it's going to continue moving from B to C, but the idea here is that there's no longer acceleration. So I can say that this is acceleration for the first segment. So let's say this is first segment, and then this is the second segment where there is no acceleration. So I can say that for the second segment, acceleration is 0. But then there's a motion at the constant velocity from B to C. Now, the idea here is you always like to write down the information that is given to you. So like, let's say, read the problem one time entirely, and then read it a second time, and then start writing down what's given to you. Some of the things, some of the information can be given to you directly, some of them indirectly. So for example, right now we are told that directly you're going to have objects starting from rest, and that means initial velocity at A equals 0. Then it's going to accelerate. So, and we know that, there's two segments, right? So accelerate, that means acceleration 1 from A to B is 1.9 meter per second square. And so technically then there's acceleration. So this acceleration, that means time from A to B is equals to 5.2 seconds. That means you have time from A to B equals 5.2 seconds. All right, so in a way, there's no other information given to you at this point. But what you're told here is you are asked to find, the speed, basically velocity, when time is equals to 2 seconds. So what is that velocity, basically? So we want to calculate velocity when time is equal to 2 seconds. Now, what do you guys think? Is this the velocity during the first segment of the motion or the second segment?
The first segment.
The first segment, right? Because we know that we are in this first segment where we are accelerating for 5.2 seconds. There's a 5.2 seconds. So the 2 seconds is less than 5.2 seconds. That means this is, when you're probably somewhere still over here and you are accelerating. And once we know that, that means we can say that this is still from A to B. where I have acceleration, I start from rest, and then I have time, which is 2 seconds, then I can, solve for the velocity at this. Let's call this some, I don't know, position D. That means, we are looking at, position D. That means we're going from A to D, which falls within this segment from A to D. Now, the important thing here about this is that you do have an acceleration. That means there's an acceleration of 1.9 meter per second square. You know that you are at rest. You start from rest at position A, and then you travel for 2 seconds. So you have acceleration, you have initial velocity, you have time, and you want to find the speed at this position B. So since you identified this to be, one-dimensional kinematics, that means you want to know, okay, so which of those equations I can use to solve for that? Remember, when you identify the type of problem, then you can kind of go and look at the formulas that deals with those type of problems. And remember, we have acceleration. We're assuming it's a constant acceleration. You have 4 equations. Equation 1, V final equals V initial plus A times T. Equation 2, delta X equals V initial time plus 1/2 AT squared. Equation 3, V final square equals V initial square plus 2 times acceleration times displacement. And then finally, equation 4, displacement equals V initial plus V final divided by 2, that is whole times time. So these are the equations for one-dimensional kinematics with constant acceleration. Remember, this is a requirement. You need to have a constant acceleration. And this is one of those classes where I usually, if I give you acceleration, it's constant. So more or less, you don't have to worry about that. So now, which of these equations I can use to find the velocity when time equals 2 seconds?
First one.
First one. See, there's also equation 3 right there, giving me velocity final. Can I use that? I don't know, I see some of you shaking head. Why not? Why can't I use that?
Total displacement of, or where he ended up. Basically.
Exactly. We don't know what is the displacement, right, from A to D. We don't know what it is. So, I mean, I have 2 unknowns. Exactly. Equation 1 is simple one. It doesn't care what's the distance between A and D. It just says that I can calculate final velocity because all I need is initial velocity, which is 0. I need acceleration, which is 1.9 meter per second square. And I need time, which is 2 seconds. So plugging those together, then I can get 1.9 times 2. I get 3.8 meters per second. There you go. That means I can just use equation 1, the simplest one, to calculate the final velocity. All right. Now, what we want to know, though, what is the speed when it reaches this position C? What is the speed? That means the speed at basically at the very end. Okay. Now, see, there's a problem right now, seems to be with this calculating the velocity at point C, because we don't know what is the distance between AB or AC. Well, technically at this point we can calculate, right? We can calculate a lot of things about A to B because we have the time, we have the acceleration and things like that. But I don't know how long it's moving from B to C. I don't know how long it's moving. But here's the thing. What did I say about this second segment? There is no acceleration over there. Now, what does it mean? It means the velocity that I want to calculate, which is at C, right? It's same as anywhere between B and C, including B. Why? Because there is no acceleration from B to C, right? That means velocity doesn't change. That means at this point, all I have to do is calculate what is the speed at point B. And that's exactly the same speed at point C. Now, how do I calculate speed at point B? Do I have all the information that I need? What do you guys think?
You would do the exact thing that you did before, but instead of at 2 seconds, you would use 5.2.
Perfect, exactly. Because at this point, again, those are good equations, but I don't need any of these equations again because I want speed without really needing the displacement. I could do like 2 steps. I can calculate displacement and then use other equations, but I don't need to right now. All I have to do is just go back, same equation, and do the same thing. 0 plus acceleration times time, but this time acceleration happens for 5.2 seconds. So then this will give me the higher speed because I accelerate for 5.2 seconds. So 1.9 times 5.2. That's it. So it's 9.88 meters per second. Excellent. Yeah, that's it. Because what happens here after we reach point B and moving at the 9.88 meter per second, the runner stops accelerating. So it moves at the same speed all the way until C. Go ahead, Tara.
This is just a quick question regarding the sig figs. Wouldn't it be 9.9?
It will be, yes.
Okay, I have to always like remind myself, don't forget about sig figs.
Yeah, excellent. Yeah, you are absolutely correct because I have two sig figs for all the values. So yes, I have to do that. All right. Okay, so this is, as you can see, right, this is this problem over here, which kind of, gives you in terms of if you have a speed somewhere and then you don't accelerate, that means you have that speed all the way, until let's say you reach the end. All right, so let's look at another example. A car is traveling due north at 23.6 meters per second. Find the velocity of the car after 7.1 seconds if its acceleration is 1.3 meters per second squared due north. So, and then second part is something different. That means what we have is this. You have a car moving, so velocity, initial velocity is 23.6 meters per second. See, because it's north, I can then put y hat, right? So then we know that's in a positive y direction. We can kind of do like coordinate system like this. Okay. Now, then what we have here is, let's say what's given to us. We also know that it's going to travel for 7.1 seconds. And then we are told for part A to take acceleration to be 1.3 meters per second square due north, so also y hat. Okay. Now, then what we want to find is basically the speed for this part A when you have these conditions. Basically, starting with the 23.6 meter per second velocity north, traveling for 7.1 seconds with this acceleration, which is also 1.3 meter per second, north, what will be final velocity? That means final velocity is unknown. And we can see, right, there is no information about displacement, but we have initial velocity, we have the time, we have the acceleration, and then we can again use the equation 1, kinematics, which is V final equals V initial plus AT. Now this for part A, then we say that V final equals 23.6 meter per second, because, right, because this is y hat, then plus acceleration, which is 1.3 meter per second square y hat, then times 7.1 second, 10 second. All right, I need to be true to the sig figs too, so sorry about that. 7.10 seconds. So then we can calculate that. All right, so that means 23.6 plus 1.3 times 7.1. All right, so I get 32.8 meters per second, y hat direction. So what it means here is, remember, right? You're given velocity north, and then you're told that acceleration is also north. So hopefully you guys remember, right? If the velocity and acceleration have the same sign as vectors pointing in the same direction, what happens here? You speed up. That's why you can see our speed is increasing if you are moving north and accelerating also in the north direction. Part B then says that, well, why don't you take for part B acceleration is 1.15 meter per second square to south. Now, how do I represent that? So it's going to be 1.15 meter per second square. How do I represent that?
Would it just be negative?
Exactly, negative y hat, right? There you go. Then we can say, all right, so then v final equals v initial plus a times time. So then this will be 23 meters per second y hat, but then minus 1.15 meter per second square times 7.10 seconds. Sorry, 23.6. All right, so then we can calculate. So 23.6 minus 1.15 times 7.1. Well, we get 15.4 meters per second y hat. And this just demonstrates that if velocity is positive, this is in the y direction, right? So vertical velocity positive, but the vertical acceleration is negative. The consequence is we slow down. And that's what happens. All right, any question on this problem?